4.6 trig identity. So with all of your trigonometry skills and your ability to solve triangles and things like that, we move into something called trig identities. So an identity, there you have room for a bit of notes at the top. An identity is an equation that is always true. Identity. An equation that is always true, regardless of the variable, the value of the variable, regardless of the value of the variable. Okay, so in the world of math and in trigonometry, there are relationships between different trigonometric statements. So again, math is simply a language used to describe or explain God's created order. There are relationships that exist, and this, what we're doing in this lesson, allows us to prove them. Certain things that we're told exist, or certain relationships that exist, certain identities that exist, and we're going to prove them. Okay, so here are a bunch of tools that you need, some identities that we're going to use, and that will help us to prove other identities. So the first one is called the Pythagorean identity.
Do these go in the lines?
Nope, okay. This is above the line still. Pythagorean identity. The Pythagorean identity says that sine squared of theta plus cosine squared theta equals 1. There's a couple things I'd like to explain here just briefly. You don't necessarily need to make notes on them, but you can if you would like. Sine squared theta is just a math way of writing this. Okay, so what's actually happening here is that you're getting the sine of theta and squaring it. And you're adding the square of the cosine of theta. Okay, so this whole putting the superscript 2 in between the cos and the value of the angle is just to clean up writing confusing math statements. Okay, so you can get rid of the brackets by simply writing it this way. It is not equal to this. Okay, this and this are not the same. This says take the angle and square it, and then take the cosine of that.
So how does
okay,
the brackets not say
this says take the cosine of theta and then square that.
But how does
okay,
the sine squared of
now
theta
this is just another way of writing this. Okay, it's not taking the square of cosine. That's meaningless. That would be like saying, oh, take multiplication squared or division squared. Okay, that doesn't make any sense.
like
All right, so, but this is just a way of writing this. Okay, now it's not this. Okay, the other thing to note is that, it looks a lot like Pythagorean theorem, right? So this is in a unit circle. Right, where you have any triangle, and what do you know about any triangle? Well, it has an x distance, represented by cosine, and has a y distance, represented by sine, and it forms a right angle triangle, where the hypotenuse is 1. A squared plus b squared equals c squared. Okay, that's all this is, but it uses trig identities. Cos sine 1. Cos of theta squared plus, sine of theta squared plus cos of theta squared equals 1 squared. 1 squared is just 1. Okay, that's why you don't see c squared.
Can we always write the second one, or do we have to write the top one?
You will only ever see this one. I'm just telling you what these pieces actually mean. Okay, and it's an identity. So what it means is you're going to be able to take bits and pieces of it and replace it with other things. You might want to actually write this as well if you have space. So because we know that this plus this equals this, what else do we know? Well, we also then know that sine of theta squared is equal to 1 minus the cosine of theta squared. Okay, if I just subtract cosine from both sides, I get another use of my trig identity. I could do the same thing for cosine. I could subtract this from both sides, and I'd get cosine of theta squared is equal to 1 minus sine of theta squared. Okay, that might prove helpful to you. There are two more to write. They're shorter. The next one is the quotient identity. Quotient identity. The quotient identity is a way of replacing tan with something that's easier to work with. It says that the tan of theta is actually equal to sine of theta over cosine of theta. Now again, that's something you already knew, because you know that the cosine of theta corresponds to the value of x, the sine of theta corresponds to the value of y, and the tan of theta is what? Y over x, sine over cosine. Okay, you've done that before. We're just putting it together and using it in a different way. So that's the quotient identity. It allows us to get rid of tan because sine and cosine are easier to work with. And then we have our last one that we've already learnt about is our reciprocal identities. Remember, an identity is a statement, an equation that's true, regardless of the value of the variable. So here it doesn't matter what theta is, as long as this value is the same as this value is the same as this value, this will always be true. Okay, for an angle of 10 degrees, this is true. For an angle of 5,483 degrees, this identity is true. Okay, reciprocal ratios are the cosecant of theta is equal to, do you know what its reciprocal ratio is? Cosecant? Yeah, so the reciprocal of sine, so you'd write 1 over sine theta. Secant reciprocal is? Cosine. Yep, so it's equal to 1 over cosine. And the cotangent's reciprocal is tangent, so 1 over tangent of theta. All right. Now you have steps. Steps to proving trigonometric identities. Okay, you have 4 bullets there. These are the steps to proving trigonometric identities. The first one is you are going to use proper format. When? Every time. How often? Every time. Even on a test? Yeah, every time. Every time. Okay, here's a reminder. It's right side, left side. That's how I'll refer to the format. You'll see it as we work through it. Good. The next thing that you're going to want to remember is you're going to want to convert secondary ratios to primary ratios. So generally speaking, if you're looking at a trig identity and you see secondary trig ratios, just like you can't solve those things in a calculator without converting them to primary trig ratios, you're going to do the same thing. You're going to right away say, oh, I see cosecant. Instead of cosecant, I'm going to write 1 over sine.
Why do you have them
Done.
at all then?
Okay? They're just ways that sides and angles relate in a triangle. What else are we going to do? Again, we don't want to deal with tan, so you're going to convert tan theta to sine theta over cosine theta. And then after that, you're just going to apply basic algebra skills. Okay, your algebra skills are necessary everywhere you go, even if you're dealing with letters and words instead of numbers, even BEDMAS. Okay, so keep those in mind. We'll refer back to those things and we'll jump into the few examples that are here. Okay, ladies and gentlemen, example 1, prove that the tan of theta squared, the square of tan theta, plus 1 is equal to the square of secant theta. First step, set it up, proper format. The left side of the equation is the square of the tangent of theta plus 1. And over here, leave some space. Okay, don't crowd yourself out and put right side like right here, because sometimes these things grow as you move down. Okay, right side here is secant, the square of the secant of theta. Now, You can work from the left side down or the right side down, whichever one you think is easier. Your goal is to make this look like that or this look like that while staying within the perfect rules of math. Okay? No cheating. All right, the first thing I see, generally speaking, you work on the left side. If you get stuck or you don't like it, then you work from the right side. It really doesn't matter. I'm going to work on the left side here, and what do I see right away? I see a tangent ratio. What am I supposed to do if I see a tangent ratio? Use the quotient identity and replace it with sine over cosine. Now, because of how squaring works, the quotient law says, so do this in a different color for a second. Quotient identity. It says that the tan of theta is equal to the sine of theta over the cosine of theta. Okay, if I square both sides, I get tan squared equals sine squared over cos squared. Okay, so it works for this as well. So here I got my equal sign. I'm working down nice and neatly. I now have the square of the sine of theta over the square of the cosine of theta plus 1. I don't need to write anything on the right-hand side. I'm just working on the left-hand side, and I'm trying to make it look like this thing. I already have secant theta. I should be thinking about what secant is. Its reciprocal is cosine of theta, right? So cos squared of theta I should have by the end. I also right here I notice, and again, these are tricks that you probably don't know right away. You're going to learn them along the way and then put them into practice as you do your practice problems. But I see I only have one term here, and I have two terms over here. So how can I get rid of, or how can I combine this into one term? I actually am going to rewrite this number 1 as a fraction. So as a fraction with the same numerator and denominator, because anything over itself is 1. So I'm going to be a little bit sneaky here, and I'm going to use a common denominator. So I'm not changing my first part here. Again, this stuff looks really tricky the first time you see it, and then after you get used to it, it becomes just a big logic puzzle. You have your tools. You say, okay, what can I do? What can I make this look like? Well, I can add these if they have the same denominator. So I'm going to replace my number 1 with the square of cosine over the square of cosine. Do we agree that that's still just 1? Yeah.
Sure.
But now, what do we have? Well, in the numerator, I have my common denominator, the square of cosine of theta. And in the numerator, I have sine squared theta plus cos squared theta. Ah, now what do you see?
You can cancel one.
Nope.
Okay, my bad. Common denominator.
Look at your list on the page of notes.
Convert tan.
What do you see?
Would you use your second?
Did you look at your page of notes? Ah, Pythagorean identity. If you still haven't looked at your notes, go look at what the Pythagorean identity is. Okay? Y squared plus x squared equals 1. So my whole numerator just reduces to 1. Okay? After you're going to use the Pythagorean identity a whole bunch. So really, as soon as you see something like, oh, I have a sine squared involved, or oh, I have a cosine squared involved, maybe Pythagorean identity is going to show up in this proof. And sure enough, you can work it so that it looks this way, and then you can apply, look how easy that became. Now you're 1 over cos squared theta, which is what? Remember, this is my goal. Can I write that step next? Yeah, it's just the reciprocal. The reciprocal ratio is secant of theta squared, the square of the secant of theta. Okay, what was that? That was a reciprocal identity. Reciprocal identity. And now to show that I'm done, I'm going to write equals right side. So now I've written that the left side equals the right side. Left side equals right side, which means I have proven it. Therefore, since I could get, without cheating, I could use perfect math and all other identities that I already know, I can prove that the left side, the tangent of theta, the square of that, plus 1 is equal to the square of the secant of theta. Done. Proper format, left side, right side. Work from one side to the other or both sides, doesn't really matter, as long as if I work down on both sides and I eventually get the same thing, then I can say left side equals right side, therefore my identity is true. Okay, set it up again. Left side, right side. Left side equals 1 minus the square of the cosine of theta. The right side equals sine of theta times the cosine of theta times the tan of theta. And already I would start looking for some connections. Okay, this one does not take too long. It's not a difficult one. I can see that I have a 1 and a cos squared of theta, 2 terms. Okay, and over here I see a sine and a cos and a tan. But I know my tan is going to turn into something else. It's going to turn into sine over cosine. Okay, and then we'll see how that works out. So here we go. I see automatically, like, also, what do you see here, by the way? Look back to your first page.
Is it Pythagorean identity?
You see a Pythagorean identity. What's 1 minus cosine squared theta?
It's 1.
Nope.
Sine squared theta.
It's sine squared theta.
My bad.
Okay, so let's go ahead and write that. And you can note that this is Pythagorean identity.
Why wouldn't we make the longer one into a shorter one?
And since that's done, I can't do anything else with that really, or at least I don't want to. I'm going to go ahead and look at the right side as well. Okay, so now we're working on both sides. What's one of the rules for proving trig identities that I see here? What am I going to deal with?
Convert secondary ratio.
Okay, there's no...
And tan of theta to sine of theta over cosine of theta.
Good, so I rewrite it. I've got the sine of theta times the cosine of theta times sine theta over cos theta. Now this is just a string of multiplication. So I actually have, if you can think about it, you have an invisible, this is sine over 1 and this is cosine over 1, and they're all being multiplied together. So I've got a numerator of sine, cosine, sine, and a denominator of 1 times cosine. Well, what happens?
You just have all
Right.
those over cosine.
Right? Right?
Sure.
Leaving me with sine theta times sine theta. What's something times itself? Squared. So I have
What's that one?
the square.
Laugh at me, guys.
I have the square of sine theta, and it's over 1. Well, that's just itself. Okay?
Oh, so it is 1.
So look, what do we have?
An equivalent ratio.
Okay, so I'm going to write left side equals right side. Therefore, 1 minus the square of the cosine of theta is equal to sine theta times cos theta times tan theta. All right? Not too hard. This is just basic algebra skills after you convert tan into sine over cos. This was Pythagorean identity, and 1 step on each side, and we had it 2 steps over here, really, if you count my crossing note. Okay, example 3, we have a trig identity with rational expression. So a rational expression just means you're in a fraction situation. You've got a numerator and a denominator. So first thing we're going to do is set this up left side, right side. Proper format. Left side is sine of theta over 1 plus the cosine of theta. And right side, way over here, give yourself some space, is in the numerator 1 minus the cosine of theta over the sine of theta. Now, I'm looking at this, and one of my favorite tools is Pythagorean identity, but I don't have any squared terms, so that's not going to work, at least not directly. But I do see something interesting. I do see a 1 plus cos theta and a 1 minus cos theta, and I'm wondering if somehow I can put those together or work with those.
Common denominator.
Yeah, it's gonna have something to do with the common denominator, that's for sure. What turns out is this looking familiar to you guys? If you have a minus b times a plus b
Yeah.
equals a squared minus b squared. Do you remember what that's called? So this is the product, multiplication, product of a sum and a difference, and it equals a difference of squares. So I'm going to keep that in my mind as we work toward here. And again, this is one of those, these are like logic puzzles. You have a lot of tools that you just need to be able to think through, and once you see it a couple times, it might be easier to do. So basically what I know is if I can get this to look like 1 plus or 1 minus, it'll be 1 minus the square of cosine of theta, I can replace that then using Pythagorean identity. I can replace that with sine squared theta, okay? So just, and that's convenient because I have that in the numerator as well. Anyway, let's take a look at what happens here. I am going to rewrite my first term here, which is sine theta over 1 plus cosine theta. And now I'm actually going to multiply by 1, just like we did in a different example. I'm going to multiply by a factor equal to 1, and that factor is going to be 1 minus cosine in the numerator and 1 minus cosine of theta in the denominator. Can we agree that this is equal to 1?
Yes.
And multiplying by 1 does not change the value of anything, okay? So this is still the exact same value, but now look at what's going to happen when I multiply bottom times bottom. I have the product of a sum and a difference. It's going to result in the difference of squares, okay? So I'm just going to work down here, and maybe I'll make a little note. What did we do? Multiply by a fraction equal to 1 in order to let's say create a difference of squares. And the point of that is so that we can use Pythagorean identity. So now if I rewrite this, in the numerator, I have sine of theta times 1 minus the cosine of theta. And in the denominator, we have 1 plus cos theta times 1 minus cos theta. Okay, that's our product of a sum and difference, which means I can rewrite this. My numerator is going to stay the same. Sine of theta times 1 minus the cosine of theta. And my denominator now I can reduce to a difference of squares. A plus b times a minus b is a squared, so 1 squared, which is just 1, minus b squared, which is going to be the cosine of theta squared, the square of the cosine of theta. Looks like this. Okay, now we have it looking how we want to. This is the hard part that you're going to have to try to remember that you can do. You can multiply by a fraction equal to 1 in order to create something that you want to see. And the reason that we would do that is in order to apply our Pythagorean identity, which is now going to allow us to rewrite the denominator. Rewrite the denominator as the square of the sine of theta. And the numerator stays the same.
How come it's a sine of theta?
So Pythagorean identity says that sine of theta, the square of the sine of theta, plus the square of the cosine of theta equals 1. That's y squared plus x squared equals 1 squared in the unit circle. It's basically this. Right angle triangle, cosine of theta, sine of theta, x squared plus y squared equals 1 squared. So that's the Pythagorean identity. And so that's what we can do here if this is true, and if I subtract cos from each side, then I get sine equals 1 minus the cos of the square of the cos of theta. Yeah. Okay, now what do you see? I have one factor of sine theta here, and I have two factors of sine theta here. So they can cross out, which leaves in the numerator just 1 minus the cosine of theta, and in the denominator leaves one factor of the sine of theta.
And they're equivalent.
Dun, 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 left side equals right side. Therefore, go back up to the beginning. Sine of theta over 1 plus the cosine of theta is equal to 1 minus the cosine of theta over sine of theta. And okay, so you are using basic identities, Pythagorean identity, quotient identity, reciprocal identity, in order to prove more complex identities. And remembering all then that an identity is a statement, an equation that is true for all values of the variable. So theta can be anything in the world, but as long as this is the same as that, theta will always be the same within an equation. But whatever it is, it can be anything, and this will always be true. So if we were talking about a 10-degree angle, this would be true. If we were talking about a 90-degree angle, this would be true. Okay? It's always true. There is an infinite number of trig identities. Okay? You only have 3 of the tools right now, plus your basic algebra skills. There are other tools that get used as you move on in this kind of thing to prove more difficult trig identities. But there are an infinite number, and you just use your basic tools, that steps that we wrote on the first page of notes, and your basic algebra skills, and then little tricks along the way like multiplying by 1. Okay? And it's just a real big logic puzzle thinking through these things. So go ahead and try that. Your practice problems are found on page 273, and what are they?
Number 8.
Numbers 3 to 8. All right.